Hey guys, welcome back. Today we're going to be talking about plate tectonics. Plate tectonics is one of the most important concepts in all of geology to understand. If you don't understand plate tectonics, then a lot of the rest of the course will be a little difficult to grasp. So make sure that you pay close attention, and if you have any questions, please contact me either in the discussion boards or by email. Let's just jump right in then. Plate tectonics. Plate tectonics was first proposed by a German scientist named Alfred Wegener in 1912. And he didn't call it plate tectonics. He actually didn't know that there were plates, but he did recognize this relationship amongst the continents, and that he believed it was the continents that were moving around. We'll talk about why he believed that here in a moment. And he called it continental drift. Today, plate tectonics is the unifying fundamental theory of geology. So just to kind of introduce our hero here, this is Alfred Wegener right now. He was a polar explorer, a meteorologist, geophysicist, just an all-around turn of the century interesting guy. You know, this at that time that was kind of the age of exploration to the poles and really, really interesting life. But he proposed this very controversial idea, and this was basically what he was proposing. I have an image over here showing continental drift over time. This is the number of million years ago, and you can follow that arrow. This is time to present. And once it gets to zero, of course this will repeat. You can see that this is supposed to be an animation of literally the continents floating around the surface of our blue planet Earth. You can see pretty rapidly why people might consider this to be a somewhat controversial approach to looking at the Earth and describing the processes that happen on it, because who would ever think that continents could move? Well, Wegener was the first one to publicly say as much. So what we're going to go ahead and do then is begin by laying out the evidence for continental drift as Wegener saw it. And we need to understand a couple of important vocabulary words going forward. First off, when Wegener said that the entire world had come together, he proposed that it was a single large continent at one point, and he called it Pangaea. Here it is right here, Pangaea. And that continent existed about 200 million years ago. He also believed that there was something called the Panthalassic Ocean, and the Panthalassic Ocean is basically one single large world-connected ocean that went all the way around this one single large supercontinent. Okay? And the reason why he believed this was because he noted right away the puzzle-like fit of modern continents. Specifically, the most obvious ones, most people see this when they're kids, South America and Africa look like they want to fit right in together. But it also turns out that North America, this edge over here, and this zone over here as we go through, it looks like a pretty good match as well for other reasons. And when you do put it all together, it actually looks like a good match. And so he went with this, and he thought that this was the explanation for what happens on the Earth, the face of the Earth changing constantly. Of course, this is a very controversial thing. Another thing I wanted to bring up, just since we have it open, is this thing called the Tethys Sea. The Tethys Sea is part of the Panthalassic Ocean, but it's right here on the edge between Africa and Eurasia. And the Tethys Sea, or at least the rocks here that are underneath the Tethys Sea, are now part of, or the area that we now call the Mediterranean Ocean, or the Mediterranean Sea. So it's geopolitically a very important thing to understand. So in addition to the puzzle-like fitting that Wegener saw, new data had come out in the 1960s that corroborated what it was that he had actually seen. And that was the fact that a lot of people noticed that the outlines of the continents didn't match exactly with each other. For example, here's South America and here's Africa. However, Sir Edward Bullard used a computer model combined with what we now know to be the edge of the continental margins. We're going to be talking about continental margins a lot as we go forward in these series of lectures. But the edge of the continents actually are a little bit underneath water. And that's what these black lines here along the coast of Africa indicate, as well as off the coast of South America and North America as well. And what that implied was that the continents were actually bigger than what they could see at the surface, that maybe there was more continental material that was available. And sure enough, once you match all that stuff up, it turns out that Africa and South America, if you match up the edges of the continents, including the submerged part of it, you have a really nice fit. And this is also true up here in Europe. Remember I said there were features. Look at this. Here's Greenland, which is part of North America. And then, of course, here's the Scandinavian peninsulas. And it fits just nice like a glove right through here. Okay? And this was corroborated using computer models. Interesting stuff, right? It's an interesting hypothesis. So the puzzle pieces seem to fit. Is there anything else? Well, yes, it turns out there's also mountain ranges that seem to match up. So when we look at modern North America here, we have the Appalachian Mountains here in eastern United States and into southern Canada. In the British Isles, we find the British Isles being Ireland right here, Scotland up here to the north. Ironically, it actually doesn't go through Britain. But you get the idea. And then the Caledonian Mountains, which also extend through the Scandinavian countries up here to the north. It turns out that they line up quite nicely when you put them back into these nice puzzle piece reconstructions. And that would be this mountain chain right here. We'll talk about why mountains might form here. But anyways, so not only do the mountains line up really nicely, but they have some other features that are important. There are similar rock types. The rocks are of the same age. And the structures on different continents correlate across. We're going to be talking about mountain structures a little bit as we go through the course. And we're going to find that some of them have interesting root structures, or they form in interesting ways, and that these structures can be found all the way through from the Appalachians and into the Caledonians. In addition to the mountain ranges, it turns out that there's additional evidence from glaciers. So there's evidence of glaciation in now tropical regions. Now, this is a very interesting thing. We can make the argument that perhaps there was a period of time in the past when a giant ice age covered the earth in ice and snow, and glaciers were going everywhere. But it turns out that that doesn't hold up, that there are some places that are now in the tropics that were covered in snow, but places that are now in snow that were then covered in tropics. So it wasn't a case of the entire Earth ever being encased in snow, at least not at that time. So that is kind of interesting. How do you get tropical areas, say Central Africa, covered with glacial deposits? These are sandstones and cobbles and things that can only get there because glaciers moved them there. The other thing that we can do is we can study glacial flow directions by the way that as the glacier goes by, it actually rips grooves and scours the rocks, and it tells us the direction. And so these arrows show us the direction of movement in modern Earth of these glaciers. So here we can see that in all these cases, they're going to the north. Which implies that the glaciers probably originated down here in Antarctica at some point. And sure enough, when you go ahead and you put together the Panthalassic Ocean, you put together Pangaea, the giant landmass, it turns out all of these glacial areas match up. And they form a nice little bullseye right around the South Pole. And they are all going away from the Antarctic subcontinent, or at this point subcontinent, but the Antarctic continent as we see it today. And it does, in fact, support the idea that there was once a very large supercontinent which had glaciers moving away from the southern pole, which is now Antarctica. And notice Antarctica hasn't really moved much, but the rest of the world has. And plant and animal fossils indicate different climate than today. There's lots of evidence that indicates that not only was the tropical regions that we now have formally in glaciers, but again, the animal distribution, say the kinds of animals that would say live in tropics now, were in very different places back then. And it only makes sense if the landmass itself moves. In addition, we find some really interesting distribution of organisms. For example, we see this fossil here that dates back to the Mesozoic, which is to say the time of the dinosaurs. It's in the western half of the Atlantic Ocean, and it's in this area that we now would consider to be southern Brazil. And then over here to the west in Southwest Africa and South Africa, we find similar fossils, if not almost identical fossils. And notice the distribution is this nice semicircle here, it's a nice semicircle here. And then there's mountains on this side and mountains on that side. What's really interesting is if we put South America and Africa together, this circle and that circle and this edge of the circle and that edge of the circle line up perfectly. Okay, so same fossils found on continents that today are now widely separated, and modern organisms with similar ancestries. Right, so we actually see common biological ancestries in areas that are so far apart that they would never have formed that way on their own. They had to be together at the time and then separated later on by mass movement of the continents. Okay, so let's talk about the actual publication when this idea came out. You would think that this would be revolutionary and that people would, take it in and think it's just the greatest thing since sliced bread. Not all new theories come out that way. So in 1915, Wegener published The Origins of Continents and Oceans. And guess what? You can still buy it on Amazon. This is the copy of, I believe, the 4th edition, if you can still read it. And you can see that he actually had a pretty good conception of what he believed, right? Here's the Panthalassic Ocean, here's Pangaea, and here you can see it breaking up. And of course, he suggested the continents plow through ocean basins via tidal forces. So one of the interesting things in science that you have to be able to do is not only come up with the observation, but you at least have to take a good guess as to what you think is causing it to happen. And he said tidal forces. This, of course, was met with hostile criticism and even open ridicule. He was somebody that a lot of really good scientists would laugh at. In the end, he wound up being right, of course, about not necessarily his mode of things moving, but his data, his observations of the continents all being together at one point. He knew that they were together. He just couldn't explain why they had separated. He was very ineffective at doing so. And so this actually was a big problem for his ideas for a long time. And the reason is the proposed mechanism defies the laws of physics. Using tidal forces alone is not going to be enough to move a continent. Heck, you can take a rock and you can stick it out in the street and it won't move the rock. And when I say tidal force, let me define that actually. When we're talking about tides, ocean tides, it's really a gravitational pull from the moon that is pulling the tides up and down. We'll be covering some of this later on in class. But in terms of tidal forces affecting continents and rocks, it's just not observed. We just don't see it happening. The laws of physics show that the gravitational attractions are just too weak to move continents. They're too weak to move standard rocks. So as a consequence, the idea was laid aside until the 1960s, and then there was new evidence from World War II. Essentially, during World War II, the Kriegsmarine, which is the German Navy, began doing high-resolution surveys of the ocean floor soon after the United States began using sonar, actually, to do studies of the ocean floor. So in addition to the sounding data of the Kriegsmarine and the seafloor studies being done by the United States Navy to be able to find the submariners in the Kriegsmarine, amazing data was collected, and we began to actually get a look at the seafloor and learn what is actually going on beneath 70% of the Earth's surface. Okay. So also, new technology enabled study of Earth's magnetic field. We're going to talk about that evidence here in terms of what it meant about dating the age of the seafloor. So the problem of how in the world you get continents to move around wasn't solved, or at least the idea of it wasn't really definitively solved until a man by the name of Harry Hess came along. Now, he was a World War II submarine captain. Remember, these guys that work in the ocean, they're looking at the seafloor closely because they're not that their ships are able to go down to the seafloor, but it makes them think about what's beneath them, I guess, when you're underneath the ocean hiding from the enemy. He was also a geologist, and he was a really good one. And what he noted was that depth recordings show seafloor features. Right? Captain James Cook made a similar observation in the late 1700s, but a lot of people didn't really take him as seriously as they probably ought to have. Harry Hess said, no, there's a lot going on down on the seafloor. It's not this big, flat, worthless expanse of land where there's just water sitting on top. There's actually got to be valleys, there's actually got to be mountains, there's actually got to be canyons, all kinds of interesting stuff. And he wound up giving us the idea of seafloor spreading. And his idea from seafloor spreading came from a notion that he had about something called mantle convection, driving the continents around. Not just the continents, but actually splitting the seafloor. And the idea is a really simple one when you think about it. As a matter of fact, here's Harry Hess. I thought I'd go ahead and point him out. And this image over here is, and hopefully this won't cover it up, but you can see this is supposed to be a heat source. And essentially what happens is you have something of equal density and you heat up the bottom part of it. It gets hot, it gets less dense, and it starts to rise. This is the reason why smoke rises. It's the reason why bubbles rise up in your soup, and you wind up, when you're cooking soup, you get these convection cells that begin to set up. And essentially they come up and they dump their heat, and when they dump their heat, they get a little bit more dense, and they sink back down to the bottom, and then they repeat the circle. And basically, they turn into a nice heat engine. And Harry Hess came up with this idea. He said, if this is happening down at the bottom of the seafloor, it's very possible that the seafloor is actually being ripped apart, and it's spreading apart at different places. Fascinating. Of course, we don't really observe this up on the continents. We'll talk about why as the course goes forward. But in the seafloor, if you're able to get a really good view, it turns out he's completely right. So the structure of the seafloor as we now know it, and based upon some of the stuff that Captain Hess had reported, was that essentially there was a convection cell that existed in the mantle. It was, as the mantle was trying to move hot material up to the top and in order to cool itself, that you set up a convection cell underneath this seafloor. And then you'll set up another convection cell underneath the seafloor, just as we just saw in that little heat engine diagram I was presenting. And essentially what this does is it brings hot mantle material up to the top, and as it cools, it forms, it'll form hot molten rock. That hot molten rock will crystallize and form new seafloor and spread out to the sides. And essentially the convection cell, by way of traction or friction on the bottom of what was basically a plate of crust that existed on the surface of the earth, would separate away from some central point that he called a spreading center. And these spreading centers would basically be characterized by a nice a nice mid-rift in the middle. And then when it spread out to the side, it would form trenches right along where it would dive back into the earth. And the reason why it would dive back into the earth is because if you're spreading it here, you can't get the earth larger. It has to go somewhere. And so it would dive right back down into something called a subduction zone. This made a couple of interesting predictions. First off, it suggested that the center of the oceans were no longer the deepest part. This had always been believed, that if you wanted to go to the deepest part of the ocean, you went to the middle of the ocean. This prediction is that, no, in fact, probably near the centers or at some point in the middle of the oceans is going to be a spreading center. And at this spreading center, you actually are going to get hot rock that sits a little higher than the cold rock around it for density reasons. And as a consequence, you're actually going to have this nice high mid-ocean ridge sitting up here in the middle. And it's going to be volcanic and full of earthquakes and all kinds of cool stuff. But the deepest part of the ocean would actually be, strangely enough, right near the land masses, right where this oceanic crust would dive down. Now, he didn't really get into the details of why it would go underneath the large land masses, but that was the prediction. So if you had a subduction zone, you'd have a trench, and that would be the deepest part, and in the middle would be actually this nice high part. Turns out he was completely right. Additional evidence came out in the form of magnetic stripes on the seafloor. So when we began in 1963 to publish and actually interpret the seafloor magnetic signatures, we had an absolutely amazing revelation about these spreading centers, right? This confirmed what Captain Hess had long been saying since the 50s. Essentially, you get a spreading center formed by magma. You get basically these arrows show that you're moving this part over here to the left, this part over to the right, and it's ripping open the surface of the earth right at this point here. And as you rip it open, magma comes in and fills in the gap. And an interesting thing happens. The earth has a magnetic field. And that magnetic field does some really interesting things over geologic time. Right now, the magnetic field points to the north. But it won't always do so. Eventually, it will flip and point to the south. And then it will point to the north again. And then it will point to the south. And these reversals, as they're so called, occur maybe every 100,000 years, 200,000 years, or several million years. It turns out there's no regular reversal rate, but it does happen. And we can see it in the seafloor, that we have periods of time where the direction of the magnetic field would be locked into the rocks because the rocks have iron in them, and it would preserve that magnetic striping or that magnetic direction. Okay? And essentially, over time, more spreading would occur. And this time, those rocks that were right here, this yellow band right here, is now ripped off to the side here, ripped off to the side here, and more magma would come in, fill in the gap in the center. But perhaps during the time that this one is forming, the magnetic field is switched, so the arrows are now reversed. And then again, the process repeats. There's another magnetic reversal. More magma comes in and fills it in, but this time it preserves the old signature. And so what happens is you get a pattern of reversals that you can see on both sides of a spreading center. So this rock and this rock are the same age, this rock and this rock are the same age, and this one here is forming essentially today. In the late 1960s, there was a deep interest in the age of the ocean floor. A lot of it was based upon how old these magnetic stripes were. They wanted to know when these things happened, so they can correlate rocks, for example, in the Pacific with some over in the Atlantic, just using the magnetic signature. They can figure something out about that. And so they went out and they started drilling all over the world. And what they noted was that, in fact, they found mid-ocean ridges. This one here is in the eastern Pacific. Here's another mid-ocean ridge due right in the center of the Atlantic Ocean. There's actually two of them that cross over here in the Indian Ocean and passes right over into this zone here. But when they looked at the ages of the rocks on both sides of the mid-ocean ridges, they noted something very interesting. That just as the stripes would show that there would be a symmetric spreading, the ages also showed that there would be a symmetric spreading. Now, this was predicted by the magnetic stripe hypothesis that was put forward in the early 1960s, in 1963. But what really blew them away was how prolific and how predictable it became. So, for example, here at the mid-ocean ridge, in the East Pacific, this is called the East Pacific Rise, actually. Sure enough, we see rocks that are between 0 and 2 million years old, basically just recently formed. And as we move away in this direction, they get progressively older to the point where the oldest rocks in the ocean are about 180 million years old. You go off in the other direction, you'll notice that there's a zone of this pink to orange color that matches the pink to orange color you find on the other side. And so that pattern tells us that the hypothesis of mid-ocean ridge or spreading centers is true. We'll notice that the symmetry here is without a doubt, right? It almost looks like a two-lane highway, one going one way, one going the other way. But it's clear that we see not only the brown the same age here, the brown the same age here, we see it here, and we see it here. In addition to the magnetic striping, in addition to the seafloor ages, there was additional evidence of what we now call plate tectonics that was coming along. And that is looking at earthquakes, which is to say earthquake epicenters, where they actually happen. And you'll notice that here is the Pacific Ocean. This whole thing here is the Pacific Ocean. But you'll notice that there's a zone of red. And these are where the earthquakes all happen. Now this again is that East Pacific rise, where the rocks are really young, and presumably this is where rocks are being created. But notice that as we move over here into Asia and Japan, that we see a big zone of red along through here, California. This is the San Andreas Fault area right here. And we see this nice zone of red. This zone of epicenters clearly marks out what we now call the Pacific Ocean or the Pacific Plate. You'll notice that there's another plate right here, beautifully demarked by all the earthquakes around it. Here's the North American Plate, again, all right here, and then right up into the North Pole. Asia, or the Eurasian Plate, same thing, marked out by this whole range. It's a little complicated over here. Here's the Himalayan mountains. Africa, fantastically interesting. And of course, this is the East African Rift. This is where part of Africa is actually trying to form its own continent. You could start seeing this forming even today. All right, so earthquakes is evidence that there's actually edges to where this stuff happens, and it correlates very nicely with what we saw. I'm going to go back again to what we saw on this map as well. So young rocks also have earthquakes, and they also seem to show really good magnetic reversal data. And so we define the global plate boundaries. In other words, the notion that the Earth is made up of, the crust of the Earth is not just a single sphere, but a bunch of plates all interlocking one with another and moving relative to one another. And that these boundaries are mappable on the globe based upon these earthquake data. So this would be the Pacific Plate here. This would be the Australian Plate. And of course it extends over here. And some of the plates are quite large. Here's North America, all the way up here. But what isn't so large is this one here. The Juan de Fuca Plate is one of the smaller ones. It's located right here off the coast of Northern California, Oregon, and Vancouver, British Columbia. Another small one would be the Scotia Plate, located down here. But again, the South American Plate and the African Plate are huge. Now, we've been able to put together some really cool data on these things. First, we notice that these arrows indicate the directions that the plates are moving. And so here we see the South American Plate is moving to the west, but the Nazca Plate over here is moving to the east. The Pacific Plate is moving to the northwest. The North American Plate is moving to the northwest. So this is an interesting relationship that results in the San Andreas Fault right here in California. And we can go on all day just on plate tectonics. Fascinating stuff. Another thing that is kind of interesting are these numbers. Here we see a 12, here we see a 16, here we see a 6. What these numbers indicate is the spreading rate. So you don't see any numbers over here because it turns out that this is where the Pacific Plate is running into the Eurasian Plate, and the Eurasian Plate is moving into the Pacific Plate. So it's not creating any spreading centers. But there is a spreading center here, right? The Nazca Plate is going to the east, the Pacific Plate to the northwest. And so we have spreading here of 16.5 centimeters per year. That's a lot of spreading. All right? The same thing is happening down here in the African Plate versus the South American Plate. They're moving away from each other at 3.5 centimeters per year. Up here in the northern part, the African Plate and the North American Plate at 2.5 centimeters per year. Absolutely fascinating stuff. So that suggests that there's two kinds of crust on Earth. There's continental crust and oceanic crust. So the continental crust is made up of less dense minerals, not really heavy stuff, things like quartz and things like feldspars, and basically predominantly granite. So here's a granite right here. So where I'm filming from here in Hawaii, granites are non-existent unless you go to Home Depot and you buy a granite tabletop, right? Other than that, you won't find granite anywhere on this island. What are some of the properties of granite? Well, it tends to float well on the Earth's mantle. It's very light. It's very low density. And as a consequence, it's home to the tallest mountain on Earth. And when I say tallest mountain on Earth, I actually should say the highest point on Earth, which would be Mount Everest. The tallest mountain on Earth is actually Mauna Loa here at the Big Island of Hawaii, not far from where I'm actually filming this video right now, actually. Another thing about these rocks is they can be quite old. It's not uncommon to get continental crust that's 2.8, 3 billion years old. You don't find ocean basins that old. The oldest rocks we find in the oceans are about 180 million years old because of that recycling we were talking about in the convection cells. So an example would be most of the North American plate, right? That would be a really good example. It also, another good example would be most of Asia, most of, Australia. You get the idea pretty rapidly. It's basically the areas sticking up out of the water. Oceanic crust is made up of denser iron and calcium bearing minerals, and basically basalt is the kind of rock that is made up of these kinds of minerals. And because it's denser, it sits lower on the Earth's surface, usually covered by oceans. It tends to sink back into the Earth when it grows old or cold. When things get cold, they get dense, right? Think about it. When you heat something up, like an iron or a piece of metal, it actually expands when it gets hot. But when it cools off, it contracts, which means it's actually denser when it's cold than when it is hot. So when it gets old, that oceanic crust gets old, it actually cools off over time and it's more likely to sink. And as a consequence, the oceanic crust recycles itself completely every few hundred million years, right? Right now, the oldest oceanic crust, again, it's the third time I've said it, but it's important, is about 180 million years old. It's also home to the deepest trenches on Earth. The Marianas Trench in the Western Pacific, bordering on the Philippines, is, or not far from the Philippines, I should say, is one of the deepest locations on Earth. For anybody who has not seen basalt, this is this black rock over here. There's a nice photo of it. So throughout this presentation, I hope you're realizing that most of the action that occurs on planet Earth doesn't necessarily happen in the middle of these large, expansive plates, even though there's some interesting things that happen there. Usually the most interesting things happen at the plate boundaries. So, we're talking about the East Pacific Rise. That's where the seafloor is spreading and creating brand new seafloor, new volcanoes and earthquakes all along that line. And on the other side of the Pacific, where the plate gets old and dives down underneath Russia and eastern China and Japan, again, huge earthquakes, large volcanoes, a lot of amazing things are happening over there. So I think it's important that we spend a little time talking about the types of plate boundaries. And there's three principal types. There's divergent plates. And essentially a divergent plate boundary is where you have two plates and they're moving away from each other. Basically because the mantle is coming up right underneath here and splitting the two plates apart. Now remember, what goes apart or whatever comes up must come down, and that leads to the convergent plates, right? Where occasionally they bump into each other. And here's one moving to the right, this one's moving to the left, and the one that's moving to the left is actually going to sink down and form a subduction zone. So here's your nice trench that formed at the bottom of the ocean as this plate went back into the mantle. The third type is the transform boundary, where we see two plates, one moving, this case, towards you, the other one away from you, if you think about these two blocks as being three-dimensional. This one moving away from you, this one moving towards you, and in between it is a sliding area where they move past one another. This is exactly what the East San Andreas Fault is essentially doing in California. The Pacific plate is moving one direction, the North American plate the opposite direction, and it forms a fault. So we're going to talk about these in detail because they have some amazing features that are very important. First, we're going to talk about the divergent boundaries, because the divergent boundaries are really what give us the most information about plate tectonics, at least in the early going. So basically there's 4 stages, and that's what these 4 images here represent. And essentially you get an upwarping of the crust due to the fact that you have a plume of hot mantle moving up, basically trying to evacuate that heat. And it puts tensional forces on the crust, and it starts to rip the crust open. So you wind up getting upwarping, volcanism, all kinds of interesting things. And over time you develop what they call a rift valley. So right here we see the crust is being ripped open from side to side. You get these fault blocks that drop down this material. Anybody that's ever been to Iceland has seen these types of features. Anybody that's actually been in the Western United States has seen similar things as well. Fascinating. The Rift Valley is essentially where the magma reaches to the surface and starts to form new crust as it fills in this gap that's formed by these 2 portions of the crust ripping open. And so over time, you get a linear sea that will form in, because the water will eventually intrude into this region and cover it up. But you're still going to see the ripping apart of the crust at this point. But in the middle, you're forming oceanic material. This basalt is coming up and filling it in and forming brand new seafloor. And over time, when you get enough distance, you'll get a continental crust on one side of the ocean, another continental crust on the other side of the ocean, and a big seafloor that extends from a mid-ocean ridge in the center with a central rift zone on both sides. And this is essentially a cross-section of North America to Africa, basically from Georgia to Morocco. Absolutely fascinating. But this is also typical of what we see in the Pacific if you want to look at things over very large scales. Some other cool features that we should keep in mind is that they form, we've already talked about the rift valleys and things like this, but shallow focus earthquakes, right? Earthquakes tend to form very shallowly there. There's not a whole lot of material underneath there that's going to break, because you got basically magma, and then beneath that you have soft, hot, gooey mantle that's convecting, right? You're not going to get a lot of earthquakes. So the earthquakes are right at the very surface. And that's a prediction that we have made as scientists, and we've actually observed that that in fact is the case, that the earthquakes do occur very shallowly in the Earth's crust at the mid-ocean ridges. So here's a map of the mid-Atlantic ridge, which goes right through the center of the Atlantic Ocean. And this is the longest mountain chain in the world. It's just completely underwater. In addition to the divergent boundaries, which are extremely important, there are the convergent boundaries. And there's 3 types. There's the oceanic continental, which is where we see the oceanic crust subducting beneath the continental crust. We have oceanic to oceanic, where we have, again, one oceanic plate, but in this case, subducting beneath another oceanic plate. And then, of course, the third type is 2 kinds of continental crust running into one another. And of course, when that happens, who subducts? Continental crust is much less dense than the oceanic crust, so it was always obvious up here who was going to win. The oceanic crust always subducted. And here, they would probably take turns, as happens in the New Hebrides of the Southwest Pacific. But continental to continental, you're not necessarily going to get a winner and a loser. You're going to wind up getting massive mountain ranges. And this is exactly how you form the Himalayan mountains, because India is coming from one direction, Asia from the other direction, and they're pushing up a giant mountain range. So there are some really interesting convergent boundary features that we need to keep in mind. First off, we need to keep in mind that convergence means that the plates are moving towards one another, right? And in this case, we see oceanic crust over here. So anything that is on the oceanic crust here is moving towards this section of continental crust over here. And that over time, the oceanic crust is destroyed. Why? Because it's literally shoved underneath the continental crust, and it begins to melt. There's basically the formation of an ocean trench that occurs here that basically shows the point where the oceanic crust is pulled under or pushed under, depending on who you ask, underneath the continental crust. and the formation of a volcanic arc. It turns out when you take a little bit of water and you mix it with rock and you bring it to high temperatures as you subduct it, it basically forms the necessary material to make magma. Magma is molten rock at very deep levels, and it forms what they call volcanic arcs, or large volcanic mountain chains on the continents. So think of the Andes Mountains of South America, right? Andean type volcanoes. In addition to that, you get deep focus earthquakes, because here you have continental crust and you have oceanic crust. They're coming in together, and you can get earthquakes all along the subducting slab, the subducting oceanic crust as it comes down. And it turns out that, of course, as you move inland, the earthquakes get deeper and deeper and deeper. Okay? Great forces are involved. It takes a lot of force to make a subducting oceanic crust happen. It takes a lot of force. And some people believe that mineral structural changes are associated. As what they mean by this is that as you push rocks down to very high pressures under very high temperatures, minerals actually begin to change and evolve. Think about diamond and graphite, right? You've all thought about diamond being made out of carbon, graphite being made out of carbon. What is the difference between the two? Well, basically what happens is that graphite put under very high pressure and the right temperature situation will form diamond. Basically what they're saying is that you might get earthquakes caused by these minerals changing, right? As the earth adjusts to the change of the minerals within it. Because some minerals are bigger, some are smaller, some have different strengths. Diamond is considerably stronger and denser than graphite, for example. So anyways, the last type of convergent boundary we want to talk about is the continental-continental convergence, right? No subduction, right? In this case, there are no winners. Two continents run into each other, that's it. They run into each other, and sometimes they keep running into each other for a while. You wind up getting tall mountains, extremely tall mountains uplifted, and you get the Himalayas from India, from the India-Asian collision. This is actually a picture of the highest point on planet Earth. That is Mount Everest right there. And what's really interesting is when you go up to the top of Mount Everest, there's actually marine fossils up at the top, because a lot of that material has been shoved up into the mountain range due to the continent-continent convergence. In addition to the convergent and to the divergent, of course, we can't forget about the transform boundary features. So the most classic transform boundary that we study as geologists, of course, is the San Andreas Fault. This is a photograph of an area just north of San Francisco, a place called Point Reyes National Park. This is Drake's Estuary. Anybody who's ever been there will think it's a beautiful place. Anyways, it's right on the Pacific, and on the one side is the Pacific Plate and the North American Plate. And in this case, one is moving down here to the left, the other one is moving up here to the right, and they're not subducting one beneath the other. They're kind of getting along. They just have to pass each other nicely, and this is essentially what's happening. That doesn't mean they don't get hung up from time to time and form very large earthquakes in the Los Angeles basin or up in the San Francisco area. But for the most part, it's a lot easier plate situation than, for example, what happens in Japan that forms the large mega tsunamis that cause so much damage. So continental transform fault, it cuts across the continent. The San Andreas Fault is a typical example. Transform faults occur between mid-ocean ridge segments as well. You can look that up in your materials that I have provided for the class, and it will describe the difference between, say, a San Andreas type transform fault and what you would see at the mid-ocean ridges. But still, very, very cool stuff. And what does it look like when a transform fault ruptures? Well, it looks like this. This is a little earthquake that has occurred, but you can see this farmer right through the middle of his field had a fault. And of course, he didn't know it was there. He plowed his field and he put his crops in there, and you could see that everything on this side is moved to the left, and everything on this side is moved to the right. Absolutely cool stuff. It does turn out that there's a lot of things that do happen in the center of the plates as well. They're just not as concentrated. For example, the big island of Hawaii is where Kilauea is currently spewing out lava every single day. And it's been doing it since the early 1980s. We're in the middle of a plate. There's no subduction happening nearby. There's no formation of a mid-ocean ridge nearby. Why do we have this here? And the reason is because we believe something called mantle plumes and hotspots. And what are these things? They're intraplate features that create volcanic islands within a plate and even island chains. Of course, we all know that Hawaii is in fact an island chain, but Hawaii is not the only one that does this. It's just the most famous example. And the beauty of these things is that they record ancient plate motions. And these ancient plate motions can be recorded in something called a nemataph, which is a hotspot track. Let's explain what a nemataph is going forward. So here's the Hawaiian Island Emperor Seamount nemataph. Here we can see the mantle plume coming up. This is basically a plume of hot magma of hot rock that forms magma down here at the bottom of the oceanic lithosphere, which then transmits material up to the surface and forms a volcanic chain. And right now, this is the big island right here. Underneath it is this large mantle plume. But if the plate is constantly moving in this direction, as is demonstrated by this arrow, you would expect to see that if this were to stay steady, not moving, but the crust above it was moving, in other words, the plume didn't move, but the crust did, that there would be a line of islands moving away. And in fact, that's exactly what we see. Here we see Hawaii, here's Kauai over here, and Kauai is 3.8 to 5.6 million years old. But there are no rocks younger than 3.8 and none older than 5.6. So that tells you that this is where the plate was 3.8 to 5.6 million years ago, that it was in fact back here, and it has since moved in this direction. Same thing with Midway. These all formed from the same hotspot and since has been dragged away. And eventually, the big island of Hawaii will be dragged up here as well. These will all be dragged up further, and new islands will form behind them. Currently, right now, the Loihi Seamount seems to be the top candidate to replace the big island as the new youngest island in the chain. So what does this look like from space? So here's an image of the Earth using Google Earth. And down here, of course, this is the big island, and here's the Hawaiian island chain. But underneath here, we're able to look using really great satellite technology. We actually have a pretty good idea of what the large features at the bottom of the ocean are. And we can see that there's a series of undersea seamounts, basically old islands, old Hawaiian islands that have since crumbled and fallen back into the ocean over time. And we can see that they come straight out off to the west, to the northwest in a straight line. This is that nemataph. That's that hotspot track that as the hotspot has stayed stationary right here at this location, the plate over it has been moving to the northwest. But notice that there's another set of seamounts that go off to the north, and they have a different direction than what we see in Hawaii. The sudden bend right here. This is called the Emperor Seamounts right here. And it goes up here and subducts underneath Russia. This is the Kamchatka Peninsula of eastern Russia. And what does this imply? Well, pretty simply put, it implies that the Pacific Plate used to go in this direction and has since changed to moving in this direction. That happens. This also indicates that plate tectonics is constantly moving the directions of the plates over time. So this indicates a change in the direction of the Pacific Plate at the time of the formation of these seamounts. And so what makes hotspot locations and mantle plumes so interesting is they explain some of the really fascinating features that occur within plate boundaries. They're not always on the edge of the plate. So when we look here at the Pacific Plate, here we see Hawaii. There's a hotspot right there. But there are other ones too. Here's one, Samoa, and a couple other down here in the South Pacific. We see them all over, and occasionally even in the continents, especially here in Africa. We see quite a few of them, and even one up here in northern Germany. Absolutely fascinating. So we actually see that the mantle, through the processes of convection, is trying to basically cool itself down, and and in doing so is driving a large heat engine that is putting mantle plumes up to the surface. It's putting huge amounts of pressure on the crust to break up and to destroy itself in some places and to form new crust in other places. The continents are, as a consequence, being floating around almost like bubbles at the top of a bathtub because they can't subduct, moving around at the whim of the mantle beneath it. Absolutely fantastic. These also explain the relationship between volcanoes and coral reefs over time. There are three kinds of reefs that we define occurring around ancient volcanic islands. Fringing reefs is the first kind, barrier reefs, and finally atolls. And atolls usually come with a large lagoon in the middle of it. Okay, this is sea level across the whole thing. And what is the difference between them? Well, a fringing reef forms when the volcano first pokes its head out of the water. The reef will form, the corals will basically live right around the edge of the island. Over time, the crust will move away from the hotspot that formed that island, leaving the reef right where it was, but over time the volcano would begin to erode and fall back into the ocean, and leaving nothing but the reef or the atoll at the spot, with just a shallow lagoon in the middle of what used to be the center of where the volcano once was. So let's make some future predictions. So assuming same direction and rate of plate motions as now we've already talked about the Emperor Seamount as changing direction. That occurred about 50 million years ago, incidentally. So not all of our assumptions are valid. But what will we see? Well, we should see that the Atlantic Ocean will enlarge and the Pacific will shrink. A new sea from the East African Rift will form from the rift valleys. The Himalayan mountains will get even taller. That North and South America will eventually separate one from another, and that part of California might eventually wind up in Alaska. And so let's see if these predictions occur. Well, there's no way of really knowing, of course, right? Because the mechanism that drives it all is down in the mantle, and we can't really see those things. All we can do is see what the response is up here on the surface. So here's a prediction of what the world map 50 million years in the future will look like. And you'll see exactly what they're predicting is South America will move to the west, North America will move to the northwest, the Eurasian plate will move up to the north, and we'll see a smaller Indian plate as it's pushed even further into the Eurasian plate. Otherwise, there's not really a whole lot that's expected to happen in the next 50 million years. Oh, don't let me forget this. East African subplate trying to break off and join basically the Red Sea right here. Anyways, I hope you found this lecture informative and useful, and next week we'll be presenting two really interesting lectures dealing with atoms and minerals and the beginning of our discussion on rocks. So hang in there. I know this is a lot of information coming at you about a whole new subject, but once we get into it and you start seeing how it all fits together, I think you're going to really enjoy this. See you next time.